All right, I'm going to walk you through Unit 4, Freefall Formative B. First off, I just want to draw your attention to the equations at the top. It's important that you understand what each equation is and when to use them. This segment here, these are the kinematics equations or the motion equations. They predict motion. And each equation, there's sort of a pair. These two go together, these two go together, and these two go together. And the only difference is the bottom one has this delta x. So instead of having x on one side, final position, and x naught or initial position on the other side, we combine them. We move this over just using algebra, subtract x naught from both sides. And instead of writing out x minus x naught equals, we wrote a shortcut variable, which is delta x. And that just means final minus initial. And sometimes those are useful when we just ask for how far has it been, or anytime we're doing proportional reasoning. Because remember, when you're doing proportional reasoning, you really don't want any pluses or minuses in there. And using this bottom row of equations when doing proportional reasoning, LT5b, can really help with that. Let's look at these equations. These equations here, those are the energy equations. Energy stored gravitationally, energy stored kinetically, and then energy transferred, or the work done. Here we have Newton's second law, so with forces. And then we have the gravity equation, Fg equals mg. Also on Earth, in free fall, the acceleration of an object in free fall is negative 9.8 meters per second squared. So make sure you are using this while you are taking your summative. Okay, let's look at LT5a. This is calculations. Problem 1, Shreya is jumping up to shoot a three-pointer. You find that her hang time, this is the total time in the air, is 0.9 seconds. How high does she jump? You really want to draw a picture with this. It will help so much. So I draw a picture and show her going up and down, and I'm going to label the time I know, 0.9 seconds, is right here. One of the tricks with solving these problems is not starting at the very beginning and ending at the very end, but actually starting about halfway through or ending halfway through. So that's what we're going to do in this problem, and I'll explain why we do that in a second. So I'm actually going to start here, and I'm going to fall down. Now, if I want to know how high she wants to jump, this is going to be a motion equation. So I got to use one of these equations here. Cross that one out because this is not constant velocity, she's accelerating. And I want to know how high, so I need to know something about position. So I'm going to need to use this equation here. I'm going to use the top one. And you could use the bottom one, but I'm going to explain it with the top one. So the final position is 0, so I'm going to put a 0 here. Now, because I'm just doing like a half problem, I'm starting here and falling down. Her initial velocity for the point that I'm starting the problem, which is her velocity at the top here, is 0. And that's why I want to start at the top there, because then this term goes away, because 0 times anything is 0. If I started here and said use the whole time 0.9 seconds, I don't know how fast she's going at the beginning, and I can't solve this problem. So this goes to 0, which is really nice. And then here is the initial position, which got moved over using some algebra. And now remember, I'm starting here and ending here. So my initial position is up at that height there. And then I can plug in some values. Negative 9.8 for my acceleration, 0.45 for the time, because that's the time it takes to get from my starting spot to the ending. So I took the total time divided by 2. And then I had an initial height of just under 1 meter. So it's telling me she's starting 1 meter above. Number 2, Emmeline Grace is practicing her hops. Her dad measures her jump height to be 0.4 meters. What is her hang time, or total time in the air? So the 0.4 meters jump height is from here to here. Or if I start up here, it's how far she fell. So it's either how high she went up or how high she fell. Again, I'm just going to want to split it in half. I'll show you why in a second. It's again looking at the total time. So you may think, oh, well, we can't use that because this is a changing velocity. We're accelerating. I could use this one now. You don't want to, because we don't know how fast she's going when she hits the ground. And we do know how high, so we're going to use this same equation again. Once again, we're going to start at the top because I know the velocity is 0. One thing you may want to do is write v equals 0 meters per second at the top there to remind you of that. So I'm going to start here. I'm going to fall down. I know that is my height from there to there. My ending position is 0. My initial velocity at the top here is 0. Again, I'm starting from the top and falling down. And I'm going to do some algebra, and I'm going to plug in my values and solve for time, and then I'm going to take a square root. Now, this is the time to get from my starting spot in this problem to my ending spot. How do you know what your starting spot and your ending spot are? It's what you plug in for your x naught and your x final. My x final was 0. My x naught was 0.4 meters above the ground, so I'm going from maximum height down. So this is the time it takes to go from this initial position to this final position. This initial position to this final position. I want the total time in the air, so I need to double it. I need to double the time because I just found 0.28 seconds and I need all the way up and then all the way back down. It's very similar to this last one, how the total time was 0.9 and I halved it just to find this part here. All right, next one is an energy one. So we have a golden retriever, jump into the air to catch a frisbee. Frisbee is 1.7 meters above. How fast is she going to need to jump initially? So like what's her launch velocity to catch the frisbee? So we know the height. And we know, we're trying to figure out how fast. And what we're going to do is when she jumps up, we're going to assume like she's not still going up in the air and catching the frisbee right here. She's going to jump up, catch the frisbee, and then jump right down. Okay, so initially, right when she's left the ground, as she leaves the ground here, whenever someone is just launching or just leaving the ground, we always say they have 0 UG. They're at the lowest point. And it's all energy stored kinetically, so 1/2 mv squared. At her maximum height, she's still not going up, so it's going to be all energy stored gravitationally, mgh. And there's nothing adding or taking away any energy, so this is 0. Let's do a conservation of energy check. I got 3 boxes here. So 3 plus 0 has better to equal 3. And it does, so that's good. So I'm just going to copy my equations here, down here for my work. 1/2 mv squared equals mgh. And then her mass is 26 kilograms. I'm solving for her launch speed. Again, mass is 26, g is 9.8, and h is 1.7. This g is positive. It's the gravitational field strength. Here, this 9.8 is the acceleration, and that acceleration points down, so it's got to be negative. But here, this field strength is just a positive number. And then we solve that, and we get her launch velocity is 5.77 meters per second. Okay? All right, we got one more. So this one here is going to be a forces one. So 16 kilogram rock falls off a cliff. Draw an FBD. Well, if it's falling off the cliff, there's no air resistance, FG, and that's it. Calculate the net force. Well, the net force is going to be mass times acceleration. There's another way to do this as well. So we're going to take the mass times the acceleration, and I know the acceleration is negative 9.8 meters per second squared because it's in free fall, and then there we get the F net. The other way to do this is to say, oh, my F net is the force of gravity. So I can do Fg equals mg. And I know the mass is 16 kilograms. The gravitational field strength is 9.8. And I know my F net is a negative mg, so I may want to put a negative out there to get a negative in there. Or I guess, there we go. Make the right side negative. Only one side, one of those to cancel out. And we still get negative 156.8 newtons. So there's a couple of different ways to think about this one. All right, that's LT5A.